All right, so 9.3 linear independent. So let me write down linear independence definition. So let V be vector space. We had a vector space yesterday. There are 10 axioms, right? So we have under the clause addition and scalar multiplication. And we learned this notation yesterday. This means a subset of V, right? Means that V is here and subset is a small part of V, right? Okay. Read subset. So if all the vectors is in subset of a V, then linearly independent, when they have in linearly independent is terminology, right? So summation I equal to 1 to n, a sub I, and vector v sub I equal to 0 vector. So implies, I want to express implies is one direction, like implies. So we have a sub 1 equal to a sub n equal to 0, right? So this means trivial solution. Okay, looking at this one, this means I can express as expansion. So a sub 1 v sub 1 plus a sub 2 v sub 2. Yeah, and a sub n v sub n equal to 0 vector, right? So this one is a scalar, right? And this is a vectors. All right. If all the scalars is 0, means that the solution is 0, right? So think about that. We had x sub 1 equal to 0, x sub 2 equal to 0, x sub 3 equal to 0, right? So that is a trivial solution. Yeah. Okay. Now they say that the set of vectors is called linearly, let me denote it this way, linearly dependent, because we are using linearly independent, linearly dependent, right? So, too many, yeah, you can read, right? Linearly dependent. 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 If it's not linearly independent. So basically, they go the same way, opposite definition and theorem, right? One is linearly independent. If not linearly independent, we said linearly dependent. We said this is linearly dependent. If not linearly dependent, we say that linearly independent. All right. So it is not linearly independent. So they are against each other, right? So they have opposite definition. All right. Okay, then since I said the opposite definition, since linearly independent has a trivial solution, then what's linearly dependent? How can you express? Non-trivial solution, right? You can express that, yeah? Non-trivial. Thank you, during my says non-trivial solution. Okay, so let us do this example. So we have S is a subset of polynomial degree 2, right? So we had this one yesterday too. So once again, this is a subset, and this is, okay, this is a polynomial, and this is degree 2, right? And most degree 2, okay? All right, so with a set of polynomials, oh, no space. Given by S equal to x squared plus 2x minus 1, 2x squared minus x plus 3, determine if S is linearly independent. Okay, look, by definition, right? So we set up everything like this, then scalar, right? Scalar, scalar, and then we say that they all should be a solution, right? So a sub 1 equal to 0, a sub 2 equal to 0, a sub 3 equal to 0, right? Okay, let's just show that. Show the trivial solution. Trivial. Okay, so we can consider this is vector v1 and vector v2, right? All right, so here we will set it up. A, the first vector, which is x sub 2 plus 2x minus 1, and plus second would be and 2x squared minus x plus 3. Okay, so they are corresponding the degree 2, so 0x squared plus 0x, and constant is 0, right? Okay, now we distribute everything, so we will get, thank you, during message, so we have ax squared plus 2ax minus a plus 2bx squared. If I make a mistake, please let me know. 3b equal to 0x squared plus 0x plus 0, right? Okay, now, thank you. All right, so we make x squared here. So a plus 2b, yeah, and x, which is plus 2a minus b, right? Okay, now we have a constant term, which is negative a plus 3b, right? Okay, there is a 0x squared plus 0x plus 0. Now we do corresponding the degree by degree, right? So we had experience yesterday or 2 days ago. Okay, so this one corresponding this one because x squared, and this one corresponding this one, and constant term corresponding the constant term, right? So we have a plus 2b equal to 0. We have 2a minus b equal to 0. We have negative a plus 3b equal to 0, right? Okay, now, so we're gonna make augmented matrix. All right, so let me see. Thank you very much, the wrong message. So we have 1, 2, 2, -1, and -1, 3, and 0, 0, 0. And then we are using reduced row echelon form. Okay, TA will give us, or can you try? Okay, thank you very much. 100, thank you so much. Thank you, Alan. And 0100000. Okay, so looking at that 0/0, right? So that's a true statement, right? And then we have just A and B, right? So like x of 1, we had before x of 1, x of 2, right? So same as here, A and B. So in that case, A equal to 0, B equal to 0, right? A equal to 0, B equal to 0. Yeah. So that means trivial solution. So we can say that the set is which is S is linearly independent. Thank you so much. Do you remember message? All right, now. Thank you, Elaine, for the reduced echelon form. Okay, now we have determined if the set, maybe we try T given below. Oh, T is the transformation, right? So I want to do this. Oops. Sorry. How about E? No, E is the elementary matrix. Yeah, I'm okay. Thank you. I dropped the pencil. So the set, oh, it's hard to make the variable. So what kind of variable would you like? Is independent. A, B, B. Okay, so we have B equal to set of -1, 0, 1. And we have 1, 1, 1. We have 1, 3, 5. So everything is about the column vector. Okay, so we want to show those are independent. Then same as earlier, we set those are equal to 0 vector, right? So we have A -1, 0, 1 plus B 1, 1, 1 plus C 1, 3, 5 and equal to 0 vector. Okay, now we converting augmented matrix, and then we do reduce the row echelon form, right? Make that. So there will be -1, 0, 1, 1, 1, 1, 1, 3, 5, and 0, 0, 0. Okay, now reduce the row echelon form. Okay, Alan gives us, so nice. We should thank him. 1 0 2 0 0 1 3 0 0 0 0 0. Okay, now we knew that this is A, this is B, this is C. Okay, so that is A plus 2C equal to 0 and B plus 3C equal to 0. Okay, which one is a free variable? C is a free variable, right? Okay, C is a free variable means we can set up anything for C. This one we had a parameter previously, right? So we can say C equal to S, or we can say C equal to T, right? Means that any number is work, right? Okay, let's say that's equal to 1 in that case. If C equal to 1, what's the B? B will be -3, right? If C equal to 1, A equal to -2, right? Thank you, Durama says. Okay, so then that's not a trivial solution, right? This is a non-trivial solution. Trivial solution means every ABC equal to must be 0, right? So this is a non-trivial solution. And if we say that C equal to 2, then we get a different number for the solution, right? So there is infinitely many solutions, right? Many solution. We call this is consistent, right? Consistent. System. Matrix. Okay. All right, then this is not linearly independent, right? This is opposite, which is linearly dependent, right? Linearly, the set T. So 3 dot is conclusion. The set I mentioned B is linearly dependent. Yeah. Okay. Now, let us talk about the dependent set. So they have lemma. So they have a proposition, lemma, theorem, right? And definition is the most strongest one. We have to follow that, right? Then next one is a theorem. Then proposition and lemma, the kind of order, right? Okay, we have a lemma. We never heard it before, right? So a little bit weaker than theorem. So lemma. So we have that dependent set. So let V be a vector space and suppose W equal to vector V1, V2, Vk is a subset of V Then this W is dependent, linearly dependent. If only if, right? If and only if, we know this word, right? V sub I can be written as a linear combination of V sub 1, V sub 2, until I wanted to make until this, okay. We've seen this statement before, right? Some vector can be written, this is the V sub I, right? So one vector can be written as a linear combination of, so we had a span of some vectors, right? That's we said that if V sub 1 is in span V2, V3, right? Then we said that V sub 1 can be written as a linear combination of that, right? Yeah, it's the same as, right? We had a yesterday. All right. So we knew what is a linear combination, but I'm gonna write that one more time. This is so we have a 1, 3, 5. We have a 2, -1, 0, 1, and plus a 3, 1, 1, 1. So we say that V1, let's say the V1, this is V2 and V3, right? So we can say that V1 is linear combination of vector V2 and V3, right? Okay, now, or since they talk about the linear combination, we can express multiple the other. Okay, so if we have vector V1, 1, 3, and if we have a vector V2, 2, 6, how do you express V1 as V2?
V1, oh wait.
V1 equal to
half of V2.
2 V2? Yeah.
Oh,
Okay.
okay.
Yes. Thank you. So there is multiple of the other or linear combination, right? Good job. Thank you very much. Okay. So let me show you geometrically. So 1, 3, 3, and 2, 6. So this is Bigger. Okay, so this is a 1, 3. This is a 2, 6. So we say that this is a multiple of the other, so linearly dependent.
Michelle, shouldn't it say 2 times v vector v1 is equal to vector 2?
Oh yeah,
Yeah.
right.
Yeah, you should write down 1/2. Yeah.
That's why you said 1/2. Yeah, thank you so much.
I was starting to go crazy there for a sec.
Yeah.
You're right. You're right. Thank you. Or we said V2 equal to
2v1.
Yeah.
Yeah.
Thank you very much. Yes. Yeah. Okay. All right. Now, we have a, let's say the U1 equal to 2, 3, and U2 equal to 5, 4. So, they're not multiple of the other, right? Multiple the other. So we say the linearly independent. Those set. So to graphically. So 1, 2, 1, 2, 3, and 3, 4, 5, 4, 4. So we have that. We have that. Linearly independent. So 2, 3, 5, 4. Okay. Now let us do this. Example, let B be a vector space. And suppose S subset of V is a set of linearly independent vectors given by S equal to UV W vectors. Let R is in subset of V be given by R equal to 2U minus W plus V new space. So I want to move this one here. Sorry about that. W, yeah, 3V plus 1/2 U. Show that R is linearly independent. Okay, so same process, right? So we want to show that there is a trivial solution, right? Okay, so we want to show this is independent. So we want to set up this one with a scalar with a sum equal to 0 vector, right? And then we show the trivial solution. All right. Okay, now A2U minus W plus B W plus V plus C 3V plus 1/2 U equal to 0 vector. Okay, now distribute to again. So we will get A2U minus AW plus BW plus BV plus C3V plus C1/2 U equal to 0 vector. Okay, which is 0, 0, right? I mean the 0. All right, now let's make a combining, right? So U and W and V. So let's see. U, what do you get? U is 2A plus 1/2 for C, U, and W minus A plus B, W, and plus B, V plus 3C. Am I right? Okay, good. All right, now let us make that. We have 2A plus 1/2C equal to 0. And we have a negative A plus B equal to 0. We have a B plus 3C equal to 0. Okay, let us make augmented matrix. So 2, 0, 1/2, 0, 0, 0, negative 1, 1, 0, 0, 1, 3, right? Okay, now we use the row echelon form. Thank you very much, Alan. So we have 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, right? Okay. Look. A, B, C. That is A equal to 0. That is B equal to 0. That is C equal to 0. They are all trivial solutions, right? Thank you very much, Alan. So it's linearly independent, right? Okay, thank you very much. Okay, now unique representation. All right, they talk about the span data 9.3.1. Let V be a vector space and let U equal to V1, Vk is a subset of V, B, linearly independent set. Okay, so linearly independent set, then linearly independent set means there's a trivial solution, right? Okay, then if vector V is a span of U, then V can be written, yeah, this is what we did yesterday, right? So this is the one. So written as a linear combination, right? V can be written as a linear combination. Let me denote it this way. Combination of vectors V, U, right? So if V is span of U, this one can be written as a linear combination of U, right? Vectors in U. Okay, now they have a lemma again. So let's talk about the lemma. Adding to a linearly independent set. Okay, we have a suppose V is not in span of U1 and UK, right? All right, that means we're gonna say opposite of this one, right? So V cannot be written as a linear combination, right? Okay, now, and the set of U sub 1, U sub 2, and U sub k is linearly independent. That means we have to think a trivial solution, right? So trivial solution. Trivial solution. Then the set so they using U sub 1, U sub 2, and U sub V. This V come from this one, right? Okay. It's also linearly independent. Okay, proof is very short. Let me prove. Prove. Okay, suppose we have a summation I equal to 1 to k, C sub I, U sub I, plus this sub, I'm sorry, V equal to 0 vector. Okay. We said that. All right. We want to show that they have a trivial solution, right? Because they say they're independent, right? So we need to show that. Okay. Now, so since we have to show that C sub I and C sub I equal to 0 and D equal to 0, right? All right, but D cannot be equal to 0. If D cannot be equal to 0, we can solve D, right? Okay, hold on 1 second. We can solve for B. If D is not 0, so solve for B. Okay, then we have, let's take a look this one. Take this one other side because we want to solve for V. So there will be dV equal to summation and negative there, right? And then I equal to 1 to K C sub I, U sub I, right? Okay, then we do divide by D, both sides. So we will have D over D. So we get V equal to minus summation I equal to 1 to K and constant the numbers. So Ci over D, and this is a vector, right? So V U sub I. Okay, now we knew that. Yeah, we knew that V is not span of the vectors of U, right? U sub I, right? So that means V cannot be written as a linear combination, right? But we did, right? So let me write down. So this is the contrary to the assumption that V is not in the span of V is not the span of U sub I, right? So this means yeah. All right, but then this is written as a linear combination, right? Yeah, this means okay, so thus equal to 0. So if D equal to 0, then yeah, if D equal to 0, C equal to 0, right? So if D equal to 0, correct? So we get, since D equal to 0, from here, let me write down. Copy. So since that So c equal to 0, right? So c equal to 0. Let me write down summation is equal to 0. The first term is equal to 0. Okay? ci ui equal to 0. Okay? So we say that since it's equal to 0, then this is implies c equal to 0. Yeah, c sub I. So therefore, this set is linearly independent. You guys okay with this?
I still need a minute to rate the last stuff you wrote.
Okay, hold on 1 second. I mean, not writing. Do you understand this? You guys understand this?
It's so upper division.
Oh, really? Ah!
Yes.
I'm so sorry. I thought this is fun. That's why.
Yeah, but the logical thinking is good. Yeah, definitely good.
It's good, right? It's
Mhm.
very good, isn't it? Yeah, this is so much fun. Okay. So done with the writing?
Wait, so the last line, it's like vector u1 comma u2, then it becomes a v, or
Yeah, because they ask us, I mean, they say that v is not in span of vector u i's, and then they set up the end. There's a set of u sub I vectors, and then u sub I until u sub k, right?
Hmm.
And they add one more vector there, which is v, which is not in the span. Yeah.
All right.
Oh, yeah. Okay. All right. So let me talk about dependent. So dependent, we talk about the multiple of the other and linear combination, right? And let me talk about one more thing. We had the experience earlier. If there is a free variable, then there is the dependent, right? Do you remember that question, the example, right? So let me add that. So dependent. Okay, so let's see. Note. So let me make a set contains more vectors than there are entries in each vector. Then the set is linearly dependent. That is set v1 to the vk in Rn is linearly dependent if k is bigger than n, right? Okay, this means n equation, we have n equation and p unknown. So we have a more unknown variable, right? So if p is greater than n, there are more variables than equation, right? So there must be free variable. So if we have a free variable, what does it mean? What does it mean? What does that mean? La, la, la. What that means? If we have a free variable.
Means we can set it to whatever we want.
Yeah, so there is infinitely many solutions, right? So we set up as a parameter, right? So we can set up parameter. So we have infinitely many solutions, right? Oops. Yeah. So which one was that earlier? So earlier we had dependent, right? So we have, this is a free variable, right? Okay, we have three unknown, yeah? And yes, they said that n equation p unknown, right? So there is more variable than equation. Yeah. So basically by column, right? So there is more column. So means that more columns. Let me write down more columns than entry. Let me write down here. More columns than entry. More columns than the entries. Okay. All right.
You don't do it?
Okay. So we have one more things. Zero vector. If a set S equal to V1 to the VK in Rn contains the zero vector, then the set is linearly dependent. Okay, so this is very short, so let me show you this one. So let's make an equation. Let vector v1 equal to 0, and we can express this on linearly linear combination, right? So we have 1 vector v1 and plus 0 vector v2 and 0 vector v3 plus 0 vector vk equal to 0 vector, right? Okay, why I'm using 0, 0, 0? it's okay, but we cannot have a trivial, so one must be not equal to 0, right? Not every a sub I or c sub I scalar equal to 0, right? Not all. Yeah, because non-trivial solution, right? Okay, so this one, we make just one number, but everything is 0, we can make that. But then look, we have a v sub 1 equal to 0, right? So we say that this is linearly dependent. This is linearly dependent. Okay, all right. Let me show you this. This one example. Like so we have 1, 7, 6. We have 2, 1, 1. We have 3, 1, 1, and 4, 5, 5, right? So we have more columns than rows, right? Entries, more columns than the entries. So it's linearly dependent. Okay, so what if we have example? So we have 1, 2, 3, and we have 0, 0, 0, and 4, 5, 6. Okay, so this is also linearly dependent because they include the 0 vector. Since zero vector. And then we had earlier the multiple of the other and written as a linear combination, right? So there is a linearly dependent, right? And non-trivial solution, right? Okay,
Oh, could you scroll up the other example you wrote real quick?
sure. This one?
Okay, yeah, that's good. Thanks.
All
Linearly,
right,
thanks.
non-trivial solution. Linearly combination, and multiple of the other. So everything is linearly dependent. Yeah, it's okay. Any question? All right, thank you for coming.